Hello, welcome to the talk. I'm Sudarshan Kannan. I am an assistant professor at Rutgers University. Today I'm going to discuss our ongoing work on redesigning abstractions for computational storage device. This is a joint work with my students, Jian and Yuji at Rutgers. First, I'll start with a basic trend in modern storage devices that's quite well known, is that modern hardware is moving towards microsecond latency era with increasing in-storage compute capabilities. To catch up, software systems are more and more trying to focus on reducing software bottlenecks. For example, designing file systems and object storage in the user space and user space drivers that bypass the OS and directly access the storage. Similarly, there are a lot of computational storage engines that is also being designed. So unfortunately, despite these advancements, still there is a dominating I/O overhead between applications and the storage layer, which results in data movement, system calls, and PCA communication costs and other overheads. So one challenge is that when we are designing new software stack for computational storage design, how can we avoid some of these overheads beyond looking at interesting data processing opportunities? So this talk is mostly going to focus on how to expose better interface for in-storage computation that can benefit both current applications and maybe future applications without substantial changes. So this talk is based on our recent work at FAST22 called FusionFS, and we have also made the code source open. So while some of these ideas are a little bit futuristic, we believe that some of the principles discussed here can be applicable for modern storage computational stacks also. So I'll start with the first trend. Even non-computational storage device, for example, like recent block devices, we see that there is an increasing number of cores in these systems. For example, some of these SSDs have like 3 to 5 to 8 Wimpy cores. Similarly, the RAM capacity is also increasing. So beyond normal basic block storage, if you see computational storage devices, their computing capability is quite high. Now, one opportunity is to run new types of computation. But the question is, can we use this computation to reduce the I/O overheads in traditional applications also? And what are the opportunities? To understand this, let's consider like different ways of storage design. In my talk, I'm going to mostly focus on like file systems, but some of these ideas could apply to object storage designs also. For example, if we take a typical kernel file system, there is an application. The application writes data to a file system that's inside the OS, which then kind of dispatches the data to the storage. Now, similarly, to overcome some of the OS bottlenecks and provide direct access to the storage, there is a lot of focus on user-level libraries and user-level drivers that use the storage directly for the data plane operation and only go to the OS for control plane operation or for some form of metadata. If you take computational storage designs, they either use kernel file system and possibly user-level file systems, but the focus is mainly on data processing. What new interesting data processing can we do inside the storage? But if we want to kind of like reduce the I/O overhead, we need to understand what form of I/O sequences do applications execute. For example, one form of simple I/O is like just do simple read or write operation. But beyond that, applications also issue sometimes sequence of I/O operations. For example, open, read, write, close. Or similarly, if you look at like other applications, they might also include some form of data processing. For example, key value stores generally use append, checksum, write, where they append the data, calculate the checksum, and write the data. And you can also take compression as an example, or like reading a block, modifying the block, and writing the block. So when we are designing computational storage engines, our goal is to kind of reduce I/O bottlenecks across all these different types of operation. Now let's look into why this is a challenging. What is the problem today? For example, if you take kind of like existing kernel file systems or maybe even user-level file systems, every time, let's say you want to read a block and modify and write it, you probably have to kind of read the data from the storage, move it back to the application, make the modification, and then write back the data. All of this incurs significant number of system call costs, PCA costs, and data copies. Similarly, if I take append, checksum, write, Even for append checksum write, you have to write the data and then make the changes and then rewrite the data again. Sorry, rewrite the calculated checksum again, and so on. And all of this again also uses significant number of system call costs, PCA costs, data copies, and so on. So a question is, can we reduce these overheads? So our approach is to kind of take inspiration elsewhere from processor designs. So we take a look at like the traditional CISC operations. Basically, CISC operations provide a capability to combine multiple operations together and kind of like delegate some of the complexities towards the hardware. So our high-level approach is that if we can combine multiple operations together and kind of offload this to kind of like a near storage engine, then we could reduce some of these bottlenecks. Of course, when you kind of batch things together, there are challenges in terms of like how much cost is each operation going to kind of take, and how do we provide fairness? Similarly, like how do you handle some form of like durability or crash consistency? What happens if I pack a complex operation and something fails? So I'll first start with discussing what do we mean by CISC operations here. So if you take a seminal processor instruction design, which is even present today, there are two widely used ISAs. One is a RISC ISA, and other is a CISC ISA. RISC ISA stands for reduced instruction set computers, which means there are more instructions. Each instruction probably takes just a cycle time. And then the complexity is delegated to the compiler to kind of compose these instructions and issue this. With a CISC instruction, ideally, the goal is that you'll have fewer and richer instructions composed of several simple instructions. Each instruction would take probably longer amount of cycles, and the complexity could be more higher in the hardware. But then the application interaction with the hardware is reduced using CISC operation. Now, there has been an ongoing debate for probably 15 years or 20 years about whether CISC is better or RISC is better. Our goal is not to get into that argument, but rather we want to see, can we take the CISC and RISC architecture designed for processor and apply it for IO to reduce the overall software dominant overhead? So if you can think about it, a RISC is like a simple instruction. For example, read a block or write a block. Whereas CISC could be then a kind of a more complex operation. For example, you can aggregate IO and data processing. For example, append checksum write or read modify write and so on. So at a high level, what we really want to do is to kind of like offload this CISC and RISC to near storage and use the near storage intelligence to kind of like make these operations so that we don't have to frequently move between the OS and the applications and the hardware device. As a consequence, if we can reduce this back and forth movement, we believe that significant amount of software overheads could be reduced. So at a high level, let's assume that if you want to do an append checksum, right? In a typical kernel file system, you have to do the append, you have to copy the data to kernel space and storage and so on, and then do the checksum and then write the data. This will also include data copies, system calls, metadata copies, and PCA cost. Our ideal goal with CISCOps is that you have a user space file systems or driver, and then you have a storage layer, and then you can just offload this complex instruction to a storage, which you're using device intelligence will do the data processing. And by doing this, we can significantly reduce the number of data copies and PCI operations and provide higher benefits. So that's our goal and intuition. Now, so in real world application, let's say, for example, a key value store, we're taking LevelDB as an example because it is kind of a base for several other key values like RocksDB and so on. But let's say in LevelDB, if you want to kind of update a block, you would kind of append data to the block and then add a CRC, calculate the CRC, and then add the CRC to the actual data. If we design this computational storage design abstraction well, we could just do a write block and then do an append CRC write and offload it to the device, and the device could do the data processing. So this is essentially our goal. So to kind of like understand the benefits and like possible benefits that we can get from this design, we designed something called FusionFS. The basic idea is that there is an application and a user level library. It intercepts IO operations from applications and converts them into sort of POSIX into NVMe commands and adds these commands to set of like IO NVMe queues. There is also a kernel component, but that's mainly for doing setup and security and so on. It doesn't come into the picture during the data plane operation. And then we have a very thin layer of storage FS inside the device, which is like a very thin layer. All it does is that simply gets the request, dispatches the request, and there is like, it could also have some form of like a IO scheduler to handle fairness across multiple tenants, and it will also have some form of fine journaling. So that's our kind of like high level approach. So to give you an example, let's say if there are two threads, these threads are operating on their own file. Here, operation 1 and operation 3 are issuing a CISC operation, which includes append, checksum, write. And operation 2 and operation 4 are issuing simple POSIX read and write. When applications issues these requests, the library converts them into set of like NVMe commands and then adds them to each file's dedicated NVMe queue. And once the storage FS is notified, it takes these requests and then runs them through some form of credential table to kind of do security check, feeds them into a scheduler, and it also has a simple journaling agent, and then it could either do data processing or do IO. So this is kind of like a high-level picture. So what you could really see here is that applications just issue one operation. We pack them into set of like array of NVMe commands and issue them as kind of like one operation. Inside, storage FS passes through this NVMe command and then issues these operations, avoid back and forth data movement. Whenever you are kind of doing batching, there are always several questions. First is that, do I have to change the application? As I showed you, for LevelDB, we required small change. But for some other applications, the changes could be a little bit more complex. So we are right now working on how to kind of develop some form of automatic offloading by deriving how these applications issue IO and automatically kind of generating them into some form of a CISC batched operation. The second question is like, what happens if I pack multiple things together and something fails? For example, let's say I want to do append and write, but let's say a failure happens after append. Now, what form of durability and crash consistency guarantee do we provide? The third question is, what happens if there are multiple tenants that are using the storage at the same time and issuing instructions that could be computationally intensive or just IO intensive? How do we provide fairness? So with respect to crash consistency, our approach is to kind of consider two forms of transaction for CISCOP. One is a macro transaction, which is all or nothing approach. And then there's the micro transaction, which does partial commits. It's all or something approach. So with the macro transaction, so the basic goal is that if I pack a CISCOP and issue a CISCOP, either everything completes or nothing completes. So for example, let's say if you take append checksum write, when you're doing an append checksum write, you do a begin transaction, and then you would append the log entry, and then you would probably do the checksum, and then write the log entry again, and finally commit the log. If a system crashes, let's say, for example, after the checksum operation, then because with an all or nothing approach, the entire transaction fails. So which means you have to recover and redo things, everything from the beginning. Now, a problem with this is that, let's say if there are 1,000 threads and all of them are issuing instructions at the same time, if a system crashes, then during recovery, you have to do a lot more processing than, and that could take a longer recovery time. So can we use like the in-storage compute capability to make this slightly better? So that helps us to explore microtransactions. The basic idea is that we could commit even the small independent operations or micro operations of a CISCOP. So for example, if we do append checksum write, we could have a transaction begin, a commit entry for a commit bit for append operation, and then a commit bit for checksum, which is an intermediate computation, and then a commit bit for write. So which means, let's say you want to do append and you want to calculate the checksum and the system crashes. So because you already have a commit bit that's already written for the append and checksum, all you have to do is like look at the commit bit, the data is already available. Upon restart, simply kind of like just do the write operation alone, and then finally kind of like go and do the checkpoint. So the basic idea is that if we use in-storage computation capability to kind of like partially commit some of the updates, then we don't have to kind of restart everything from beginning, and that could significantly reduce recovery time. The next challenge is like what happens if there are multiple tenants that are issuing IO intensive operations. Some of these operations could be computationally intensive. Some of these operations could be intensive in terms of memory usage. So our inspiration is to kind of take something from like the compute schedulers, like for example, CPU schedulers, like completely fast schedulers, and apply it for computational storage device because they're also doing IO and computation. So for example, let's take an example of like how do we apply the CFS here. So let's assume that there are two files. Thread 1 is accessing file 1 and it's doing like IO intensive operations like up and CRC write and checksum read, checksum write. File 2 is just doing basic IO operations. In our design, every file gets its own IO queue. So which means instead of the storage level scheduler thinking about the clients and the applications and other things which it doesn't have visibility to, all it needs to do is like find out how much of compute each queue is using, and then based on that provide some form of fairness. So for example, if file 1 is present in the NVMe queue or the inode queue here, maintain some form of a CPU virtual time here. So let's say if the first queue, which is like file 1, is using computationally intensive task, maybe we can say, okay, now it's time to give the CPU, the compute capability to file 2, which is using lesser CPU, make them run for some time, make them complete some operation, and then give back the data, give the CPUs back to the first queue, which is more computationally intensive. So the goal is not to say here that use CFS, but the goal here is to say that when we are thinking about computational storage design, which also uses computation, provide some form of fairness across multiple tenants and come up with some better scheduling that not only takes into consideration IO scheduling, but also takes into consideration the amount of computation we use. So this problem could also happen for memory, where memory could be a precious resource inside the storage device, and there could be some form of contention and starvation. So we could also have a CFS scheduler for memory, but maybe there is a better technique to come up with, a better scheduler to come up with this. Okay, next, while we didn't have a computational storage design device where we can completely change the firmware and all the layers, what we wanted to do was at least get some form of kind of an emulated performance kind of trends. So to kind of design that, we designed an emulated in-storage file system as a complete dedicated device driver, which lives its own space. It has its own dedicated CPUs. The CPUs are completely throttled to lower frequencies. Their memory is also throttled to lower frequencies. And for all the operations, we include PCI operation. And we compare this design against the state-of-the-art kernel file systems, for example, ext4, which is a direct access ext4 DAX, and Nova, which are direct access file systems for NVM. We also take SplitFS, which is a user-level file system, and compare it against our design. First, we want to understand this notion of CISCOP, which essentially combines multiple non-identical and identical operations together. Do they provide benefits? For our analysis, on the x-axis, we use this up and checksum write workload, and we vary the number of threads. On the y-axis, we have the throughput. As you could see, even for this up and checksum write microbenchmark, our system provides significant performance benefits. That's because we are reducing this back and forth data movement. If you take our paper, we also kind of compared this performance by like varying the CPU frequency. What if we reduce the CPU frequency to even something lower? And we saw that even when reducing CPU frequency, we still see benefits, because at the end of the day, the cost of all the software overheads is way, way higher compared to the frequency at which some of these operations are run. Again, we cannot generalize this for all the operations. Some operations probably require heavy CPU activity. So the choice is like essentially how much of computationally intensive task that we are going to run inside the device. So even for the read, modify, write, we see the same performance. Just for our curiosity, we wanted to also see like what happens if we like forget computational storage design and offload this CISCOps to just like the kernel file systems. So we just offload this CISCOps so that we can reduce back and forth between application and the kernel. Of course, this would not reduce the back and forth between the kernel and the storage, but just to kind of see here, for ext4 DAX, we added this CISCOP, and as you can see, even for ext4 DAX, we see good performance benefit by avoiding back and forth movement. These results are kind of reflective even in like some of the well-known macro benchmarks, like say varmail, web server, and file server. On my y-axis is throughput. As you could see, even on these kind of like workloads, there is some benefits by reducing frequent back and forth movement. Finally, we wanted to kind of understand the performance in real-world applications like LevelDB, which are not just doing I/O, but they are also being computationally active. We have also done it for RocksDB, but for the interest of time, I'm not going to go over because they're pretty much similar. Essentially, we offload for every write, we offload the append checksum write, and similarly for read operation, we kind of like offload this to the near storage computation. On the y-axis is the value size, and the x-axis is the throughput. We compare our approach against like different user level and kernel file system. So even for a real application, we see some good performance benefits. If the value sizes are really large and if the computational requirement is very high, then probably adding more compute cores to the near storage device would provide even more benefits. That's our kind of intuition. So to summarize, when we are designing computational storage, software for computational storage, it's important to kind of think about not only what new or cool data processing operations we can run, but also how is it going to impact the overall system state? How can we reduce the data movement across multiple layers? And how can we use the in-storage layer, not only for data processing, but also for like other aspects like I/O? So our solution is to kind of like combine these operations into some form of like a CISC-styled operation, and come up with like better kind of like scheduling across multiple tenants and provide some form of crash consistency. And we see that there are some good performance benefits, while they might not directly translate into real storage, but we still believe that because of these fundamental principles, we'll still probably see these trends. And we wanted to kind of like rethink this organic design without significantly changing the application. Of course, as we kind of like explore more and more application, we'll see like what are the challenges. But we believe CISCOP is a kind of a good first step when we are thinking about like abstractions, even small changes to the NVMe commands by kind of including some form of a vectors of NVMe commands could be useful. We believe that I'm happy to have more discussions with industry to see like if there is some form of like a more practical solution that we can come up with. We have released the source code also if you're interested. Feel free to kind of like either ask questions in the chat window or please send me an email. So with this, I conclude my talk and thanks for listening.